All right. Cool. So we're going to go ahead and do another AP free response. This is 2009 Form B, AB free response 1. It is a calculator question. At a certain height, a tree trunk has a circular cross section. The radius r of t of that cross section grows at a rate modeled by the function dr dt equals 1/16 times the quantity 3 plus sine t squared in centimeters per year, from 0 to 3, where time is measured in years. At time t equals 0, the radius is 6 centimeters. The area of the cross section at time t is denoted by a of t. All right, part A. Write an expression involving an integral for the radius r of t from the window from 0 to 3. Use your expression to find r of 3. Okay, so this is that first fundamental theorem of calculus question, just with a little bit of a twist. So before we start, I'm going to go ahead and advise that the very first thing you do is go ahead and put this in as your y1 in your calculator. So 1/16 3 plus sine of x squared, close the parentheses. So I did use x instead of t because I'm not in parametric mode. So you should be in radian, and you are probably in function mode because this is APAB, not APBC. Me personally, I always like to put my fractions in parentheses. You don't have to, but that's just the way I roll. So 1 divided by 16, and then in parentheses 3 plus sine of x squared, close the parentheses, right? So so my stuff looks like, so first off, check that you're in mode radian and function. I put my y equal stuff in there. I did that because I know preemptively I'm going to need to use my calculator to integrate at some point in this problem. You don't have to do it. It's not part of part A quite yet. It's just useful to do. So I know that this is the rate. So let's do a quick review again about that first fundamental theorem of calculus. I'm going to inch this guy this way a little. Okay, so remember, we've seen the first fundamental theorem of calculus before. It says that if you integrate some f prime of x from a to b with respect to x, you get f of b minus f of a, right? And what we've seen when the AP asked this question, which is a lot, right? The AP asked this question a lot, is that they're going to give you some f prime that you can integrate in one or two ways, right? Maybe it's a function that you can integrate by using geometric shapes on a graph. Maybe it's a function like this that you can make your calculator integrate. One of those two options is usually what's going to happen. And then they're going to give you either f of b or f of a, and then you're going to find the other one, right? So here we are given the radius at 0, which is 6. So we are given, in this part A, right, we are given that r of 0 is 6, right? And they want us to find r of t, right? So this is one of those tricky questions where you're going to have to use a variable as one of the bounds of integration. So if you were to integrate, right, so if I were to integrate from 0 to t of this dr dt, right, this 1/16, 3 plus, remember that if you're integrating with a variable as a bound, you have to pick some other letter. So I'm just going to go ahead and pick x since I was using it anyway. You have to pick some other letter for in here. This thing is going to equal big R of t, right? Just like when you integrate f prime, you get f, minus big R of 0, which is totally a quantity that I know. So if I want big R of t, my answer to part A is going to be that R of t equals whatever R of 0 is, which in this case is 6, plus the integral from 0 to t of that 1/16 3 plus sine of x squared with respect to x. Notice that, again, if a variable is one of your bounds of integration, you have to make sure that you use a different variable of integration. So because I'm using t as a bound, I had to use x. I used x here. I missed a set of parentheses, sorry. I used x. Sometimes they use a different letter. You can use pretty much any letter that has not already been assigned in the problem. So you can't use t, you can't use r. I would not use a because they use a for area. All right, so that's my r of t. Then I'm asked to use it to find r of 3, which is actually the easier question, right? I'm going to make my calculator integrate from 0 to 3. So this is what my calculator is going to have to do, right? This is what the calculator is going to have to do. So they don't care about this. All they care about, they understand that if you did this part, you did the math. So all they really want here is they want you to type and find the answer. So this is a 6 plus, I'm going to use function integrate in my calculator, right, which is math 9, y1 with respect to x from 0 to 3, right? And when I do that, I'm going to get an approximate value out. It's going to be 6.601, or 6.611, and it's a radius, right? So it should be centimeters in this problem, right? So that's the answer the AP cares about, right? They just want that R of 3 is this. They don't care about any of this stuff in the middle. They care about this piece because they asked you to find it, and they care about R of 3 being this value. That's it. Okay, so part B. Find the rate at which the cross-sectional area is increasing at t equals 3 and indicate units of measure. So, I think I'm going to have to use this again. I'm just going to throw that out there. I'm pretty sure I'm going to have to use this again. So, again, if I show you how I put this in my calculator, right, it's a 6 plus math 9, right? Vars, I go to y vars, I pick y1, comma, with respect to x from 0, comma, 3, there we go, and I get this value. I'm going to store that as alpha a. So I suspect that I'm going to have to use this again. And I might not have to use it again, right? But it can't hurt to store that as a so that if I need it again, I have it, right? So I'm going to go ahead and store that as a. So now that I have that, let's talk about b. And remember that R of 3, so I'm just going to make a note somewhere on here that R of 3 was stored as a in my calculator for my purposes, right? So when we start to do b, again, just for my own personal, sad, tragic memory, I'm going to make the note for my brain that I stored R of 3 as a in my calculator, right? Just so that I don't forget. Okay, so I'm given that a of t, right, is the area of a cross-section of this thing. So we know the area of a circular cross-section should be pi r squared, right? So that's what the area of this thing should be. They ask me for the rate of change of the cross-sectional area. They ask me if the rate of that the cross-sectional area is increasing, so the rate at which the cross-sectional area is increasing. So that's going to be a prime of t, right? So if I want a prime, this is the part I have to math by hand. I can make my calculator do the number crunching, but I have to do the actual work by hand. That's going to be a chain rule. So when I derive this thing, I'm going to drop the 2 down in front and get 2 pi r of t quantity to the first, which I don't have to write the 1, times the derivative of r of t, which is r prime of t. They don't want the derivative all the time. They only want the derivative at 3, which is 2 pi times r of 3. Oh, look how convenient that I stored r of 3 as a in my calculator, times r prime of 3, which is totally a number I can find by plugging in 3. So what I'm going to type in is that this is 2 pi a times whatever happens when I plug in a 3 here, which would be a 1/16 3 plus sine of 9, right? And then I'm going to get an approximate value. I'm going to type that in my calculator, and I'm going to get that it is 8.858. And then they ask me for units. So keep in mind that a prime is the same as dA over dt, right? That's what a prime means. So in this problem, area would be measured in centimeters squared, and time would be measured in years. So this is centimeters squared per year. So that's the rate at which this thing is increasing, is 8.858 centimeters squared per year. That's part B. Okay, let's do part C. C, evaluate the integral from 0 to 3 of a prime of t dt. Using appropriate units, interpret the meaning of that integral in terms of the cross-sectional area. My bad. All right, so, and you might need this value. It might be worth storing that guy as b. It doesn't hurt if you're never sure if you might need another answer again. You could have stored the 8.58 as b. I don't think you're going to need it again. So for part C, we're asked to integrate from 0 to 3 of a prime of t. So this is actually another callback to the first fundamental theorem of calculus. That's going to be a of 3, because when you integrate a derivative, you get the actual function, minus a of 0. Well, this is the cross-sectional area, right? Cross-sectional area at t equals 3. And this is the cross-sectional area at the start, right? Cross-sectional area at t equals 0. So even if we don't know off the top of our heads instantly what this means, or I'm sorry, what the actual value of this is, we know that what this means is the increase in the cross-sectional area. This is essentially how much the cross-sectional area grows from when you started at 0 to when you end, right? So I can find these values by plugging in what I know, which is that a of 3, right? We know that from the previous problem, a of t is pi r of t quantity squared. So that means that a of 3 is pi times r of 3 quantity squared. Well, aren't I happy again that I stored that as a? That was my answer to part A. And A of 0 should be pi times whatever the starting radius was, which was 6, so that should be a 36 pi. So essentially, I'm going to type in my calculator, A squared pi minus 36 pi, right? And the reason I say A squared is because that's what I stored my R of 3 as. So if I do alpha A squared, right, and then pi minus 36 pi, and hit enter, I get 24.200 or 201. So I end up getting that this is 24.200 or 201 centimeters squared, right? And what this is this is the growth of the cross-sectional area from t equals 0 years to t equals 3 years, right? So this is how much the cross-sectional area grew in that 3 years, okay? Cool. And